Valves are found in every industry, from paper manufacturing to petrochemical processing. They come in all shapes and sizes and are as varied in their uses as they are in their design. Some valves may be operated by hand, while others require complex automatic regulation. Every valve, though, has one thing in common. They all control the flow of fluid. In this program, we'll explain how different valves regulate fluid flow, and we'll show you how to operate valves in the safest, most efficient manner. In this first segment of the program, we'll be looking at globe and gate valves. The gate valve controls flow by placing a movable metal gate across the pipe's opening. When the valve is fully closed, the gate is lowered all the way into the opening and the flow is stopped. When a valve is throttling, it controls the flow rate by restricting the amount of fluid that can pass through the valve. Gate valves are not generally used for throttling service because throttling causes high pressure to develop at the base of the gate, leading to excessive wear. In this cutaway gate valve, we can see its 5 basic parts: the body, the bonnet, the gate, the stem, and the hand wheel. The valve body can be attached to the piping by several different methods. Flanged piping may be attached to the ends of the valve body with bolts. A gasket is inserted between the flanges to prevent leakage. The bonnet and the body are also fitted with a gasket and are bolted together. In this gate valve, a hand wheel attached to a stem moves a gate up and down. The stem passes through a stuffing box located in the bonnet. A material called packing fills the stuffing box and seals off any gaps that might permit leaks. Toward the top of the valve, the threaded stem screws through a stem bushing, which is firmly attached to the hand wheel. Supporting the hand wheel is an outside yoke. The hand wheel turns freely but stays connected to the yoke. As the hand wheel is turned counterclockwise by pushing with the right hand and pulling with the left hand, the stem and attached gate rise and the valve opens. Turning the hand wheel in the opposite direction, or clockwise, closes the valve by lowering the stem and gate. Because of its design, this is called a rising stem valve. You can always tell if the gate is open or closed by looking at the position of the stem. Some rising stem valves aren't threaded at the top. The stem in this type of rising stem valve is threaded on the bottom, and it engages threads on the inside of the bonnet. The hand wheel and stem are solidly connected, so both the hand wheel and the stem rise together as the valve is opened or closed. In this type of valve, there is no outside yoke attached to the hand wheel. Some gate valves have stems that do not rise. The stem of this valve is solidly attached to the hand wheel. A collar at the bonnet end holds the stem in place. It cannot move up or down. As the hand wheel is turned, the stem screws into or out of the gate, raising or lowering it. The position of a non-rising stem valve cannot be determined by looking at the stem or hand wheel. There are different types of gates that can be used in gate valves. The most common ones are the parallel disc, the solid split gate, and the solid wedge gate. Gate valves have a matching set of seat rings located within the body of the valve. As the valve is closed, the gate descends between the seats and makes a tight fit, sealing off flow. Wear and friction occur where the gate and seat rings come together, which can result in leakage or make the valve difficult to open. The second type of valve we will look at in this section is the globe valve. The design of the globe valve does not allow flow to pass through in a straight line. The valve seat is set parallel to the flow, so the fluid must change direction as it passes through the valve. Globe valves are frequently used for throttling service because their parts wear evenly when partially open. In the throttling position, all of the disc and the seat ring are exposed to equal flow and pressure, so any wear that occurs is likely to be even. As a result, complete closure is still possible even after long throttling service. A globe valve is usually set up for throttling so that the flow is from below the plug, which tends to open the valve. This provides a more stable operation and eliminates slamming or closing as the plug nears the seat ring. Flow from the other direction would put pressure on the top side of the plug and could close it. Globe valves can be equipped with several types of discs, including the plug disc, the composition disc, and the conventional disc. The plug disc is the most common globe valve disc, and it comes in a variety of styles depending on its service. Composition discs are made of a flexible rubber-like material so that hard particles from the flow will not prevent a tight closing. Conventional discs are constructed of hard materials like metal or ceramics. Contact between the two hard surfaces will often break up particles deposited by the flow. Let's review how gates and globe valves are designed and used. Please stop the tape and turn to Workbook Period 1. In this section, we will look at some other valves commonly used in industry. One of these is the plug valve. The plug valve uses a handle to regulate flow. When the valve is open, fluid passes through an opening in the plug. A quarter turn of the handle rotates the plug 90 degrees and closes the valve. Because the flow travels in a straight line, there is very little resistance to flow through an open plug valve. Although plug valves are generally used for on-off service only, they can be equipped with an erosion-resistant plug that makes throttling service possible. A close fit between the plug and valve body is necessary to prevent leakage, but the close fit can result in excessive wear from friction. For this reason, plug valves have to be periodically lubricated. Another type of valve, called a ball valve, operates in much the same manner as a plug valve. It employs a ball with a circular hole to control flow. The ball rotates between two rings. In the open position, the flow is straight through. A quarter turn of the handle rotates the ball 90 degrees to close the valve. Ball valves are primarily for on-off service. In the throttling position, high fluid velocity will rapidly erode the partially exposed seat ring and the edge of the port opening. A ball valve, however, can be adapted with a special plug that makes throttling service possible. The plug is positioned off-center in relation to the seat ring so that it won't make contact with the seating surface until shutoff is complete. This allows equal flow around the full area of the plug even when the valve is only slightly open. Because flow and pressure are distributed equally across the plug, the valve can be throttled without excessive erosion. The operator can determine if the ball valve is open or closed by looking to see which way the groove at the top of the stem is pointing. When the valve is open, the groove runs parallel to the pipe. Closing the valve rotates the groove across the line of flow. Sometimes, however, the stem breaks away from the ball, so don't bet your life on the position of the stem. Use proper line breaking or blanking procedures and be skeptical around quarter-turn valves whose stems indicate they are closed. Here is a butterfly valve. Butterfly valves control flow by using a flat disc that rotates within the body of the valve. When fully open, the disc presents little resistance to the flow. A quarter turn of a handle, though, rotates the disc fully into the process stream and stops all flow. Butterfly valves can be used for both throttling and on-off service. Because dynamic forces develop across throttling butterfly valves, they should always be latched into the throttling position to prevent them from slamming open or closed. Nearly all the throttling capability occurs in the first 30 degrees of rotation, so be aware that there may still be a lot of flow through a butterfly valve that is only 1 or 2 notches open. Here's a valve that doesn't use a plug or a disc to control flow. It's called a diaphragm valve. Flow is controlled by a plunger that moves a flexible diaphragm up and down in relation to a weir or seat. The diaphragm forms a seal that prevents fluids in the line from entering the working parts of the valve. So, this type of valve is ideal for handling corrosive fluids, sticky materials, or other substances that require high purity. Valves that control flow direction rather than flow rate are called check valves. Although check valves come in many different designs, they all provide the same basic service, which is to prevent the reversal of flow in piping systems. This is a swing check valve. The disc is free to move on its pivot pin either toward or away from the valve seat. As long as the flow is from A to B, the disc will flip away from the seat and allow fluid to pass through the valve. If the flow were to reverse itself, the disc would swing down and close the valve. In the lift check valve, the disc and seat design is similar to the design of a globe valve. As flow occurs from A to B, the disc moves upward. But if flow stops or reverses itself, the disc moves down and closes the valve. So, lift check valves also control direction of flow. Because gravity pulls the disc downward when flow stops, a lift check valve cannot be installed vertically or in any other position where gravity cannot do its work. If installed vertically, the valve will still admit flow, but it will not close if the flow direction changes. For this reason, this type of valve is called the horizontal lift check valve. This is a vertical lift check valve. When the flow from A to B stops, the disc drops back to its seat. Flow from B to A can't occur. The vertical lift check valve can't be installed horizontally. Flow, pressure, and gravity also operate ball check valves. Instead of a disc or gate, a ball controls the opening of this valve. Ball check valves are manufactured in both horizontal and vertical designs. Now, it's time to review the material we've just covered. Please stop the tape and turn to Workbook Period 2. Good working order. Before operating any valve, make sure you're wearing the proper personal protective equipment. The requirements here may vary depending on what service the valve is in. The minimum requirement, however, will usually involve some type of eye protection, goggles, or a face shield. In some situations, it is not practical to operate a valve with just a lever or a hand wheel. Some large industrial valves can be operated with a motor that is attached to the valve stem. The motor produces the power needed to position the valve and at the same time increases the opening and closing speed. By using remote control, one person can operate several motor-driven valves at once. A large valve requiring a lot of power to operate does not necessarily require a powerful motor to do the job. If a system of gears is attached, the power needed to operate the valve is reduced, and the valve can be positioned manually. Sometimes valves must be located in areas that are hard to reach. When this is the case, an extension stem or a sprocket wheel and chain can make the valve easier to operate. Regardless of what type of valve operating mechanism is used, valves should always be opened and closed gradually. This will prevent sudden pressure and temperature changes from occurring in the piping. For example, if a valve is suddenly snapped shut, the abrupt change of flow causes pressure surges that can damage the valve and, in extreme cases, even rupture the pipes. This is known as hydraulic shock and is primarily a problem in lines controlled with quick opening valves. Some large valves are often difficult to open because one side of the flow control element is under much more pressure than the other side. These valves are usually equipped with an equalizing line. The valve on the equalizing line is always open before the main valve. This allows pressure to equalize on both sides of the flow control element, making the large valve easier to operate. Sometimes a valve will become stuck because the moving parts are corroded, excessively worn, or fouled with solid materials. In these instances, it may be necessary to use a valve wrench or cheater to operate the valve. Wrenches are available in a variety of different styles and sizes. To prevent damage to the valve, check the manufacturer's specifications concerning the wrench use before using a valve wrench. Choose the correct size wrench and securely attach it to the hand wheel or spokes so that the wrench will not come off when force is applied. When applying force to the wrench, make sure your weight is evenly distributed so you don't fall when the valve opens. Wrenches should always be pulled towards you to prevent ramming your fingers when the valve gives. If you encounter difficulties or have any questions, notify your supervisor. When closing a valve, you should avoid using excessive force because this may damage the seats or the flow control element. This is especially true for gate valves in high temperature service. After the valve is closed, it cools and the valve body contracts. If the gate is already jammed into the seats, contraction of the valve body may cause the gate to bind. Many valves, such as gates, plugs, and globes, require periodic lubrication for smooth operation. On outside stem and yoke valves, the exposed threads should be cleaned and greased at regular intervals. The internal valve parts are usually lubricated with a grease gun or by inserting a stick lubricant into a special fitting. All valves with stems have a stuffing box that is filled with a sealing material called packing. The packing material is compressed by a gland to produce a leak-proof seal around the stem. If packing leaks occur, they can often be corrected by tightening the packing gland nuts. Eventually, however, the packing will be compressed to its limit and will have to be replaced. Leaks sometimes develop between the valve body and the bonnet, or the piping. These leaks are often caused by a gradual stretching of the bolts that hold the various parts together. They can usually be fixed by simply tightening the bolts. Whenever you're dealing with leaks, avoid contact with the leaking fluid because it can and often does pose a hazard. Let's review the material on valve operators and operating procedures. Now, please stop the tape and turn to workbook period number 3. So far in this program, we have mainly focused on valves that are operated manually, either by hand or by motor. In any manufacturing or process industry, however, there are applications where it is desirable or necessary for valves to operate automatically. When automatic operation is desired, a control valve is used to regulate the flow of fluids. The body of the control valve can be designed like any of the manually operated valves we discussed earlier in this program. But instead of a hand wheel or a lever, a control valve is equipped with an actuator that moves the valve stem. The actuator receives commands from a controller telling it how to position the valve. The controller sends signals in the form of compressed air, hydraulic fluid pressure, or electricity that automatically move the valve into the desired position. This control valve is powered by an actuator that receives compressed air signals from a controller. The actuator contains a diaphragm and a spring. Air pressure from the controller tries to push the diaphragm down. The spring tries to keep the diaphragm up. When air pressure against the top of the diaphragm exceeds the force of the spring, the valve stem is pushed downward and the valve closes. This type of actuator can be used for both throttling and on-off service. In some instances, the maximum compressed air signal from a controller is not able to move the valve stem fast enough or hold it in a steady position. When this is the case, a valve positioner is installed on the valve to help the actuator position the valve stem. Here's another type of control valve. It has a solenoid actuator. The solenoid consists of a spring, a coil, and an iron core. Electrical signals from a controller move the valve. When electrical current is sent through the coil, a magnetic field is set up that pulls the core upward and closes the valve. When the current stops, the core is pushed out of the coil by the spring and the valve opens. Because of its design, a solenoid-operated valve can only be used for on-off service. Solenoid valves with heavy springs find important duty on fuel supply lines to boilers and furnaces where they snap shut quickly if electrical power fails or other safety trips are activated. If throttling action is required, a motor-operated actuator can be used to position the valve. The motor is connected to the valve stem through a system of reduction gears and is capable of moving the valve into any desired position. This control valve is operated by a hydraulic actuator which contains two chambers that are separated by a piston. When more hydraulic fluid is directed into chamber 1, the piston is moved to the right and the valve closes. Directing hydraulic fluid into chamber 2 pushes the piston to the left and opens the valve. Hydraulic actuators can provide on-off or throttling service. Most control valves are equipped with some type of valve position indicator. These indicators are usually attached to the valve stem so that an operator can quickly determine the actual valve position. In this program, you've seen the various types of valves that can be used in piping systems to control the flow of fluids and gases. We've looked at how these valves are designed and discussed what kinds of service they are set up to perform. We showed you mechanical valve operators, such as gears and sprocket wheel and chains that can make a valve more accessible and easier to operate. You also learned some basic operating procedures that should be followed when opening and closing a valve. Finally, we introduced you to valves that operate automatically in response to a signal from a controller. These control valves are positioned by an actuator which is powered by compressed air, hydraulic fluid pressure, or electricity. This concludes our program on valves. Now go to your workbook and complete the final section. Thank you for watching.